Now we're going to move on to something which I think is pretty neat, and it addresses something we've said kind of for a while, which is that electric and magnetic fields are really kind of the same thing. So that's a good question. How can an electric and a magnetic field be the same thing? So let's go to our setup. So the first thing we'll do before we get into the details of how they're the same thing is let's remember about relative motion, relative velocity, and reference frames. So if I'm walking along and I have a cup of coffee in my hand and someone asks the question, is the coffee moving? I would say that the answer to that question depends on who you ask. According to me, the coffee is still because it doesn't move relative to my hand or my body. But according to somebody else, the coffee is moving. The coffee and I are both walking along. Same deal if you're holding a water bottle in your car while you're driving. To you, it's still, but to the people outside, it's not still. So we're going to talk about that kind of relative velocity, but we're going to address that idea to charges. So our setup is going to be, we have two people. Alec, we'll call him A. Brittany, we'll call her B. So we have Alec and Brittany. Alec makes a magnetic field. I'm not quite sure how. He may hold up a couple of giant permanent magnets. Brittany, she's holding a charge in her hand and she's running through this field that Alec has made. Okay, so there's our setup. Alec makes a magnetic field. Brittany is hanging onto a charge Q and she's running through it with some constant velocity. So now the question is, who sees what? Okay, so let's ask who sees what. Let's ask what Alex sees first. Alec is looking. He sees a magnetic field because he made it. He sees Brittany holding the charge, so he sees the charge moving. So Alex sees that charge Q is moving in a magnetic field. We know that the result of that is that there's a magnetic force. You can find the direction of the force. You put your thumb in the direction of velocity, your index finger in the direction of the magnetic field, and your index finger shows the direction of the force. That force is upwards. So that's what Alex sees. But then you can also ask what Brittany sees. Brittany has the charge in her hand. She's running, but to her, the charge is not moving. So she can't see a magnetic force because as far as she's concerned, that charge is not moving. So that's kind of a problem. Is there a force on the charge or is there not a force on the charge? Can we say Alec is right or do we say Brittany is right? How do we decide? Um, so let's ask a question. Is the charge accelerating or not? If we have an inertial reference frame, if Brittany is running at constant speed, then we should 100% agree on the force. But so far, we don't agree on the force. So let's see what we're doing. So we've said, and what Alex sees, is that the magnetic force depends on the velocity, but we never really asked the velocity with respect to what. Okay, so that's an important question. So let's move on to a recap of relative velocity. So let's think about that, and we'll approach it in kind of a first-year physics sort of way. So let's start with our first frame of reference. That'll be Alec. And Alec we're going to call the ground. So Alec is stationary. Okay, so we'll start there. Next we'll add in Brittany. Brittany, she's B. We'll color her red. Brittany is moving. We are going to stipulate that Brittany is running with a constant velocity. And we can call Brittany's velocity of Brittany relative to Alec. And that's the kind of notation we would use in first year physics. Okay, so we've got Alec as ground, Brittany is moving with her velocity. Let's bring our charge in. So we'll call C our charge, and our charge is moving. A charge has some velocity, and we could measure the velocity either relative to Brittany or relative to Alec. Both are valid things to do. So we can do that. Let's write down our relative velocity equation. Let's write down the velocity. Let's write down the relative velocity equation. So our relative velocity equation says the velocity of the charge relative to Alec is the velocity of the charge relative to Brittany plus the velocity of Brittany relative to Alec. That's kind of the familiar relative velocity equation. So VCA is VCB plus VBA. It's like the B's in the middle cancel and you're left with CA. So there's our relative velocity equation. What we could do to this equation, because we said they should agree on force, is let's take the derivative of the whole equation. So if we take the time derivative of the whole equation, the derivative of c to a plus the equals the derivative of c to b plus the derivative of b to a, the derivative with velocity with respect to time, that's acceleration. So now we have a relative acceleration equation, a relative acceleration equation. Let's put in one more thing that we said at the beginning, which is that Brittany is running with a constant velocity. So Brittany's acceleration has to be 0. Okay, so that part is 0. That means that the acceleration of the charge relative to Alec is equal to the acceleration of the charge relative to Brittany. Alec and Brittany agree on the acceleration, so that's good. Now, what does that mean about force? Well, we know that force is mass times acceleration, so if they agree on acceleration, then they must agree on force. So what that says now is that Alex sees a force on the charge, Brittany also sees a force on the charge, and those forces have to be in the same direction and they have to have the same magnitude. So they 100% agree on that there's the same force. So now let's talk about the force from each one of the points of view. So what's going on from Alec's point of view? Well, Alec made the magnetic field, so that's the x's here. Why don't we label that guy in? So this is the magnetic field made by Alec. That's a vector, so we'll call that a vector. There's the magnetic field made by Alec, so he definitely sees a field. He sees the charge moving with a velocity relative to him. So that charge Q moves with velocity of the charge relative to Alec, which means he sees a force on that charge, and that force is the magnetic force. And that has to be his conclusion, that it has a magnetic force that points up. So why don't we even draw in that magnetic force? And we get the direction of the magnetic force that Alex sees by using the right-hand rule. Thumb goes with velocity, index finger with B, middle finger shows the force. So Alec 100% sees an upward force on the charge, and he calls it a magnetic force because the charge is moving in a magnetic field. So that's what Alec sees. What does Brittany see? Why don't we talk about her next? So we established that Alec and Brittany agree that there is an upward force on the charge and that those forces have the same magnitude and the same direction. However, Brittany does not agree that it's a magnetic force. Brittany says that the charge is still. That means that it can't be a magnetic force. But Brittany is thinking there's a force and there's a force on the charge. What kind of force does that have to be? Well, it must be an electric force because charges feel electric forces. So if Brittany says there's an electric force, what kind of field does Brittany think there is? Brittany thinks there's an electric field. The only way to get an electric force is to have an electric field. So there's an electric field in Brittany sees that there's an electric field in her vicinity. Alec thinks it's magnetic. Brittany thinks it's electric. And she says there must be an electric field because there's an electric force, because she agrees that there's a force. So Brittany and Alec 100% agree on the force, but they describe it in very different ways depending on what they see, what their experience is. Brittany sees that it's an electric force, which is equal to Q times the electric field, and I put a B on the electric field because it's the electric field seen by Brittany. Alex says it's a magnetic force, which is QV cross B, and there's an A on the B for magnetic field because it's the field that Alex sees. So they both see a force, but they describe it in two different ways. So you gotta ask the question, who's right? Is it a magnetic field? Is it an electric field? How do you differentiate? Because they both say that they're right. Well, the answer to that question is they're both right. Either description is valid. They're both right and they're both true. So what can we do about this? Let's say that the magnetic force is equal to the electric force because they've agreed on those forces right from the start because it's an inertial reference frame, which means that V cross B is equal to Q times E, which brings us to the conclusion that the electric field is the velocity crossed with the magnetic field. When Brittany runs past Alec, the magnetic field that he makes turns into an electric field, right? From Brittany's point of view, it's an electric field. From Alex's, it's a magnetic field. So whether or not a field is an electric field or a magnetic field really depends on your point of view. So it depends on what you're doing. So that's such an interesting concept, and Maxwell used these kinds of ideas when he was developing his equations to talk about the speed of light and light as an electromagnetic wave. So that's really neat, and we just couldn't let the course go without talking about that. So then the next thing we'll do is we'll probably come back to circuits and we'll do some inductors for a while.